morning. Good morning, everybody, and welcome to Math in the Morning. So today I made some slides for degrees of supercompact cardinals, and I'm still going to wait on the proofs, the killing them softly proofs for measurable and supercompact. So also I was thinking, I'm making these slides now. The talk is February 18th, so I have some time to really think about what I'm going to say and just be really familiar with the topics. Okay, so how was your weekend? I hope you had a good weekend. I'm really happy to be here, and I had a good weekend. I made a video of I got some clothes. I went shopping. So I usually go shopping I don't know, maybe once a year. I like to go to the thrift store a lot and pick things up. I got some clothes for professionalism. Okay, so let's look at these slides. Okay, so the first slide is degrees of supercompact. These are all very similar to the measurable case. So it's really just a slight tweak of the measurable case. So in this picture, we're going to fix the theta. So we're going to focus on your theta supercompact. So it means you're the critical point of a non-trivial elementary embedding, and also you can see M theta is a subset of M. So any sequences of length theta, and theta is between kappa and j of kappa, any sequences of length theta with elements of M is in M. Okay, I would like to talk more about that, but I'm not going to do that right now. But I would like to talk more about that, and I'd like to talk more about normal measures and fine measures. So another definition of theta supercompactness is that there's a normal fine measure on p kappa theta, and p kappa theta is the subsets of theta that are size kappa. Okay, so I'd like to have a whole thing. Maybe we can, I can put off the proofs a little longer. We could maybe do that tomorrow, maybe not, I don't know. But I'd like to just do a little bit about what's normal, what's fine, and what's p kappa theta. What do these things look like? What does it mean for M to be closed under theta sequences? What does that really mean, and when does that happen? When does it? What could happen if that? What could it look like if that doesn't happen? Okay, so I'd like to do a whole day on that. I feel like I had some thought that just escaped me. Oh yeah, I'm gonna make some joke about we're gonna find out what's normal and what's fine. So I don't know. I wish I knew what was normal and what was fine. I'd like to be fine. Okay, so the degrees of supercompact. So this is Mitchell rank 2 for theta supercompactness. We can see he's got the rank 2 on his shoulders. He says I'm a rank 2 theta supercompact cardinal. So you can see he's a little different than a measurable cardinal. You can see more, and he's rank 2 because in M, we can't see this yet, but in M, there's in M, kappa is theta supercompact, okay. And it's not any rank bigger than that. So if we want to be exactly rank 2. Okay, also, I was thinking, as a philosophical point, I feel like maybe am I joking? I don't know. I mean, all this stuff is actually very interesting and very philosophical, but, you might be is the kappa to think about, I'm sure people think about this, is the kappa in V the same as the kappa in M? Really? I'd say, kappa is theta supercompact in V, and he's also, referring to the same person. Is it the same person? I don't know. Okay. So rank 2 for theta supercompactness means that you're theta supercompact. There's elementary embedding witnessing that, and look at all the elementary embeddings witnessing that. And there's at least one where kappa is theta supercompact in M, but it's not anymore theta super. It's not rank 2 or anything like that in M to be exactly rank 2. Okay, so that's that one. I have these kind of out of order on here, so I have to just check. Okay. So degrees of supercompact cardinal. Next slide. A cardinal kappa has. With Mitchell rank 1 for theta, so the way also there's the notation in the way we say it. So okay, so I haven't gotten the notation yet. So cardinal kappa with Mitchell rank 1 for theta supercompactness means kappa is theta supercompact, but it's not theta supercompact in any target model M in any embedding witnessing that kappa is theta supercompact. Okay. A cardinal kappa has Mitchell rank 2, so Mitchell rank 0 for supercompactness would mean it's not theta supercompact at all. Okay, there could be some disagreements on that. A cardinal kappa has Mitchell rank 2 for theta supercompactness if kappa is theta supercompact in M, where J from V to M witnesses that kappa is theta supercompact, and kappa has rank 1 in any such M. So, or you could just say cardinal kappa has at least Mitchell rank 2 if there's some elementary embedding witnessing that it's theta supercompact J from V to M, and it's also theta supercompact in M. That would be at least rank 2. So you can see it's really just similar to the supercompact, the measurable case. Okay, so let's see this picture. Okay, next slide. Okay, so this is you can see here in this slide, you can see the notation. It's like order of kappa, like measurable, but there's like a subscript that says theta SC. So that's theta supercompact. Okay, I'm just thinking about strongly compact. Okay, so order theta supercompact of kappa is 3 means you've got this one guy from J to V to M. He's the critical first point moved. And he says, "I'm theta supercompact." You can see he's got the glasses on. He's got the rank 3. And then in M, this is over, and this is like the greatest instance of this happening. It might happen other places. It has a little bit of supercompactness in M. This is like all the M's. This is the greatest instance of theta supercompactness. And okay, so in M, kappa is for the critical point of an elementary embedding, ultra power embedding, J from M to M prime, and kappa says, me too. I'm also theta supercompact in M. And then this guy, I said you don't have to make the joke. You can just say me too. You don't have to say me 3, but I can't control these things. Okay, so he says, hey, me 3, I'm theta supercompact in M prime. Okay, and then it stops there, and he's not anymore theta supercompact. He's exactly theta supercompact with no higher rank. You can see his shoulders has the rank 1. Okay. Okay. So the next slide. So again, the Mitchell order, the Mitchell rank for the Cardinals comes from the Mitchell order on the measures. Okay, so we can think of the Mitchell order for normal fine measures on p kappa theta. So suppose kappa is theta supercompact and let mu and nu be normal fine measures on p kappa theta. Okay, so it's theta supercompact, and these two measures are both witnessing that it's theta supercompact. So we'll see if they fit inside each other. Define the Mitchell relation for theta supercompactness as mu, and then we've got the order symbol with the only difference is now for Mitchell rank for supercompactness, you have like a theta SC notation. So mu is order less than nu, and this order is well founded. If, just like before, if mu is in M sub nu, where J from V to M sub nu is an ultra power embedding by nu. Okay, so where mu is in M sub nu. Okay. So order theta SC of mu is the rank with respect to this relation. Okay. So order of kappa equals alpha means that the height of this relation on normal fine measures on p kappa theta is alpha. Okay, so you can imagine these measures sort of building up. Okay, and then what's next after that? The last slide is, okay, so finally just like the official definition, degrees of supercompact cardinals, our theta is fixed, the order sub theta SC of mu, let's say the Mitchell order for this measure, this theta supercompactness measure rank. Sorry, I did that. Okay, so it's supremum. So I'm jumbling the words, but it's the supremum of all of the orders of all the nu that are less than it in this Mitchell relation plus 1. And then so that finally the Mitchell rank for theta supercompactness for kappa is the supremum of all of the orders of all the measures in M kappa. And M kappa is the collection of normal fine measures on p kappa theta. And p kappa theta is subsets of theta of size kappa. And so I just like to insert a picture there for normal and fine. Normal means that you're closed under diagonal intersections, and there is kind of a nice picture with that. And then being fine, this is from Cantor's Attic. F is a fine filter. If for every A and S, one has the set of all X and S such that A is an X is an F. I'd like to draw a picture for that, so I'm going to leave that space there for those pictures. Definitely diagonal intersection, you can see something. Okay. So it'll be nice to be able to go back and forth between like the elementary embedding definition and like the normal fine measure definition. Okay. Especially the proofs. Also, I feel like it's a little more understanding if you're like talking about the normal fine measures. Okay, I'd like to just have a solid picture for both those things. Okay, we went over the time a little bit. Okay, thanks you guys so much. It's so motivating to come here and talk about this stuff. I feel like this week I'm gonna get it done. The slides, I hope so. The slides for this talk, and then if I do get done, I might take a break from this so I can like. This is fun when I have something to show you. This is fun when I have a slide to show you. But if I'm just sitting here thinking about something, it's like it's not so. I don't have anything to show, so it's kind of like, oh, this is what I thought about. But I'm just saying that for sure this week I'm gonna keep doing this, and then we'll see what happens next week. Okay, I don't want to like commit myself to something. This is supposed to help me get ready for my talk. Anyway, thanks you guys so much for listening and being around, and yeah, hopefully maybe you can come to my talk. Okay, see.